Well, your work at Next Lab sounds amazing, especially from the perspective of a college student. Can you tell me more about this project and what it might mean for the future of nuclear?
It's an exciting project. We're working to build a university research reactor, the first new reactor in 40 plus years in the US. And it's a new technology. And so we're looking to how can we make the safest and cleanest form of energy safer, more clean, make it more affordable. And so that's the exciting future that we're hoping to build into.
That's awesome. Now, could you describe to me the way a molten salt reactor works in the way that maybe a 10-year-old would understand?
Sure. So we have a heat source, and how do we move that heat from one place to another? And a place where it's generated to a steam generator where we make steam, and the steam goes to a turbine, turns a generator, and makes electricity. So all we're really doing is we're changing the heat transfer fluid. So what carries the heat from the reactor to the steam generator, instead of using water, which has some advantages, we're using a different fluid, and that fluid is salt in a liquid form, so we call it molten salt.
Great. Why is salt more efficient?
So it's more efficient because it allows us to operate at high temperature and low pressure. High temperature is good because we're more efficient in producing electricity at higher the temperature you start with, but the low pressure means there's not the safety hazards around. If a pipe bursts at high pressure, boom, it sprays all over. If it's a fluid like water that wants to do a phase transition to a vapor, now you have high temperature, high pressure vapor moving up in the atmosphere. And if that liquid has the potential of having radioactive material in it, then you've just distributed radioactive material around the world. Think about what happened in Fukushima, right? If we replace that water with molten salt, if there is ever a leak, what happens? Well, it stays in liquid form and gravity pulls it down to a catch pan underneath it. So it drips down to catch pan. As it cools down to room temperature, it becomes a solid. So any radioactive material inside of it is encased in a solid right there.
That sounds incredible. No, molten salt has been a concept for years, right? But there's been a struggle to implement it on a commercial scale. Do you think your research will change the game?
I sure hope so. I think, early on there was sort of two ideas competing. There was the water-cooled reactors and there was salt-cooled reactors. And the first heavy customer, the developer that did that first heavy lift for the technology was the Department of Defense. They needed nuclear power for submarines. They even considered airplanes and other applications. But a water-cooled reactor in the middle of an ocean isn't necessarily a bad idea. It was when we took that and we said, oh, let's just stop our development and let's commercially deploy that technology. Well, we can do better. And current reactors provide us with lots of clean energy, but we can do better. And so it's time to innovate again.
Yeah, innovation. Now, from what I read, you didn't consider a career in nuclear until late in high school after attending a seminar about fusion. Is that right?
Yeah, you did some research to find that story, I guess. So, yeah, I went to what's called Texas Energy Science Symposium when I was in high school, and I just got enthralled by this idea of limitless clean energy. And really, what really got me excited, although I couldn't articulate it this way at the time, was the really high energy density, right? If you're working with the strong force, you can have a very small amount of fuel and produce a great amount of energy, so you have the minimal impact on the environment. And so if we care about the planet, that's what we're looking for.
Yeah.
And so where can we invoke the strong force and get energy out? Fission is proven, it's there, it's understood, but we can do advanced fusion. Fission. I said that wrong, didn't I? Fission. Great. Fission is proven and deployable. We can do better and use advanced fission type. Fusion, of course, is a great idea, and somewhere in 100 years, when we figure it out, let's use it.
What do you see as the biggest challenges for nuclear education today? And is there enough of it? Is it publicized enough? Like, why don't we encourage kids to become nuclear physicists like we do astronauts?
Well, I mean, I think great question, and I think we need more nuclear education. There's, of course, always the high glamour positions that young children or students can look to and get excited about. But more often than not, you really look to your parents or your near mentors and follow in their footsteps more than anything. And so just having a lack of nuclear engineers in the workforce today means that there's not that immediate role model. And so you do have to have the ability to project what that profession looks like. But maybe more important than that, there has to be a career, a future out there.
Yeah.
And for decades, there was really no future in nuclear engineering. It was just all the nuclear engineers were doing was maintaining the 50-year-old technology and slowly shutting down reactors, right? But now all of a sudden we find ourselves in an environment where we value clean energy, and we want to quit burning, hydrocarbons. And so in that environment, nuclear is really the only answer there if we want reliable, clean power.
Yeah, what would you tell someone who wants to pursue a career in nuclear innovation?
The future is going to be nuclear powered. The world is committed to a carbon-free future. The world also is committed to a standard of living that's not sustainable from unreliable sources. And if we really care about the environment, we have to go with nuclear. So the future will be powered by nuclear. And so the sooner you jump in and get at the front of that wave, the better.
It just makes sense.
Just makes sense.
Now finally, what do you think is the coolest thing about nuclear power? Why are you so into it?
It makes the world a better place, right? I mean, the mission of Next Lab is to develop the technology of molten salt reactors to leave the world in a better place than it is today. A lot of times I say its purpose is to bless the world. Can we develop medical isotopes to help cure cancer? Can we produce high temperature industrial heat that can desalinate water and do things like that? Can we produce energy that's affordable, clean, abundant, and safe? If we do those things, we're going to bless the world, and the world will be a better place than it is today.
Atoms for peace.
There you go.
Right.
Absolutely.
Well, that's all the questions I have. Thank you so much.
Thank you.